Symmetry with respect not to the x-axis or the y-axis, but to the origin. This is a little bit harder to visualize, but the strategy is simple. If any point x, y is on the graph, then negative x, negative y has to be on the graph. When I looked at the y equal to 2x plus 3, one of the points I got was 1, 5. I can pick any point. One of the points that works is 1, 5. What does that mean has to be on the graph if this thing is symmetric with respect to the origin? Negative 1, negative 5. So the question is negative 1, negative 5 on the graph?
And when you get a complement thing, is it going to look like what you do both,
Why did I do 1, 5? I just picked a point that we had already chosen out of this graph, 1, 5. And you could start fresh again. You could go, okay, let's let x be 2. 2 times 2 is 4 plus 3 is 7. So 2, 7 is a point, which means that negative 2, negative 7 would have to be a point.
So you would start at just
I start at any point. Start at any point that's on the graph that works. See if basically the opposite point, the negative x, negative y, is also on the graph. So let's see if it is. Let's substitute negative 1 for x. See if I get negative 5. Substitute negative 1 for x. Negative 2 plus 3. That's 1. So negative 1, 1 is on the graph. So my conclusion is that the graph of this equation is not symmetric
To the origin.
to the origin, with respect to the origin. Yes, ma'am?
Would it be the same if you were just to plug the negative 5 in and the negative 1 and work it all the way to the bottom?
Yes,
If they don't need to?
sure. Yeah, you can absolutely do that. You can say, hey, does negative 1, negative 5 work? Let's find out. That's my x, that's my y, let's substitute. Negative 5, question is, does this equal 2 times negative 1 plus 3? Negative 5 equals negative 2 plus 3? No. Negative 5 is not equal to positive 1. Another way to do it. So substitute the x and the y, see if you get a true statement. Good question. Is that okay? So we got 3 kinds of symmetry that you're going to be questioned about. Webassign-ish. Okay? So when you get to your Webassign, I think there's at least 2 problems like this that say, here's an equation. Is it symmetric to x-axis, y-axis, origin? Or more than one, because it could be symmetric to more than one. And let me show you this guy. Imagine that's a circle. Imagine that's a circle with its center at the origin. Is that symmetric with respect to the y-axis? Yeah, divides it perfectly in half. Is that symmetric with respect to the x-axis? Yeah, divides it perfectly in half. Is that symmetric with respect to the origin? So for every a, b, is there a, negative b? Yeah. That's an example of something that's symmetric with respect to the x-axis, the y-axis, and the origin. Okay? So it can be symmetric to more things than one. And speaking of circles, let's speak of circles. Because that's one of the things that we're going to be asked about in this particular... Oh, one thing I should point out. Before we leave our line here. This has 4 points that we found. 1, 5, 2, 7, 0, 3, 3, 9. Hey, is the point 5, 12 on this line? How you gonna find out? Plug it in. Substitute x, substitute y, see if it gives you a true statement. You're going to have 3 problems like this on WebAssign. You're going to be given an equation, and you're going to be asked, is that point on this graph? I don't know. Do I have to draw it to find out? Absolutely not. Just substitute 12 for y, 5 for x. See if it gives you a true statement. 12, does that equal 2 times 5 plus 3? Well, does it? No, it doesn't. So if I get a false statement, what do I know about the point 5, 12? Not on the graph, not on the line. Okay. So you're going to have opportunity to do that multiple times. Here's an equation. Here's a point. Is that on the graph of this? Is that on the graph of this particular equation? Substitute. The true statement it is. The false statement is not. Okay. Let's go to our other picture, that of a circle. If I was going to describe a circle for you so that you could draw it precisely on the graph, in fact, you would draw exactly the circle I have in mind and none other, what would I have to tell you about that circle so that you could draw exactly what I have in mind? The radius, that's how big it is, right? And the center, that's its location on the graph. Okay? If you told me, hey, draw a circle as big as a 50-cent piece, I go, okay, is that the circle? You go, no, that's not the circle. Okay, is that the circle? How about that? Is that the, how many circles are there the size of a 50-cent piece on this graph? Oh, come on, you know the answer. Infinite number, right? Just move the center around and I got another circle the size of a 50-cent piece, right? What if you told me, okay, I'll tell you where the center is. It's right there. Can I draw the circle?
No.
How many circles are there that have that as its center?
Infinite.
Infinite number. I could draw one with a very small radius, a larger radius, a larger radius, a larger radius. What are those kind of circles called with the same center? Concentric circles. Absolutely. And there are an infinite number of concentric circles with that as the center. So the size is not enough, the center is not enough, but you give me the center and the size, and I got it. So what do I need for a circle? I need the center, and I need the radius. Now, if you thought diameter, or if you thought circumference, that's the same idea as the size, but we're going to use radius because that fits into our equation for a circle. Now, some special notation. Anytime you talk about the point that is the center of a circle, you don't use XY. You use HK. Kind of snooty, I know, but you use HK. So that when you see HK, you know I'm not just talking about any point on that circle. I'm talking about that one point that defines the center of the circle. So when we talk about the center of a circle, we'll use HK. When we talk about the vertex of a parabola, we'll use HK. HK is that very specific primal point in a particular graph, like a parabola or a circle. And what